The components of a modern electronics device, or as I call it on this channel, an embedded system, are connected through what's called a printed circuit board, a PCB. And when working on an embedded system today, you will come in contact with PCBs, even as a software engineer, especially during the stage referred to as board bring up, which is what I'm going to talk about in this video. Because after the PCB is designed, the day will come when the manufactured boards finally arrive, which is an exciting time on one hand, because there is nothing like the smell of fresh boards, but on the other hand also stressful, because there is a high risk there are mistakes in the design, and these needs to be discovered and fixed so that new boards can be ordered as soon as possible. Exactly what board bring up entails in practice will of course vary, but the overall goal is always to ensure that the hardware works as intended. Typically, assuming a larger team, the first thing that's going to happen when these boards arrive is that the hardware engineer gets hold of the boards, and they will likely do some preliminary inspection and maybe some electrical measurements. They could, for example, check that the components are mounted correctly and gets the power as expected and whatnot. But then once the hardware engineers are done, maybe after having patched the boards, the software engineers get hold of the boards. At this point, the software engineers hopefully have had some time to prepare some software that can be flashed to verify that the board is working. And this software may toggle GPIOs and send stuff over common communication interfaces such as SPI, I2C and UART to pinpoint any incorrect connections. Of course, then as the design is finalized in later revisions, there will be less and less work required to bring up the boards, because there will be less changes made between the different revisions, and there will also be more code in place. I myself, as you know, developed a sumo robot a while back, and this is what I've used in this video series to demonstrate embedded systems programming. It also has a PCB, and this means that at one point I've also had to do bring up of it. But so far in this video series I haven't actually used this PCB, but instead I have written all code using the development board for the same microcontroller. But in this video it's finally time to move over to the actual PCB. In other words, it's time to do board bring up. Although it's going to be a bit of a fake one, since I've already verified that this board works. Also, for this board bring up, I'm further along with the software than you usually are at this stage. I mean, I basically have all the drivers in place, as well as a list of tests to verify them all, and a separate build target for the actual PCB. And this should, in theory, make the board bring up go very smoothly. Though there may be some code mistakes I've made that I need to fix in this video. Okay, so here is the actual robot, and here is the PCB. And if this was for real, I would probably do some visual inspection here first. But now I'm just gonna skip that step and go straight to powering up the board. Okay, good, no smoke, that's a good sign. And the LED lights up, which is also good, because this means that I have power. And this was actually not the case when I got the first revision of this board, because this board is the second revision. And when I got the first revision and I powered on the board, the LED didn't light up. And the reason for that was because I had accidentally oriented one of the diodes the wrong way around. But fortunately that was easy to patch. But then I also made another mistake on the first revision, and that was the connections to these two motor drivers here. I had mixed up the input signals to these motor drivers, and that was a bit more of a hassle to patch. I don't think I even patched it and just did a new revision, because the footprints are pretty small, so it was hard to patch. But in general, when you get a new board that has some issues or hardware issues, and you think you have a pinpoint what is wrong, you should always try to patch the board to actually confirm that that is the issue, and try to patch the board as far as you can, so that you can actually confirm what is wrong before you spin a new board revision. Anyway, after powering up the board, the next natural step is to try to flash some software onto the microcontroller. And by doing that, I can verify that the microcontroller is up and running and that the debug interface works. Note, on this design, I don't have a proper debug connector. And instead, I just connect some wires or jumper wires from my launchpad and use the debugger on the launchpad instead. Okay, so now I'm just going to build my software for the actual PCB, the NSUMO target. And then I'm just going to try to flash that to the microcontroller. And yes, that seems to work. So that means that the microcontroller is up and running and that the debug interface also works. So that's a good sign. Then in order to know what I need to check next or what I need to check during the bring up, I must understand the hardware. And to understand the hardware, it's probably best to refer to the schematic. So I can open up the schematic. Okay, so here is an overview of the schematic, and doing board bring up is really just a matter of verifying that the connections and the ICs on this schematic works as intended. And from this schematic I can basically extract a checklist that I can go through during the bring up. And as I said before, fortunately during this video series, what I've done, I have written all of the code necessary to test the different parts in this schematic, which is going to make it quite easy to run through this checklist during this video. And I want to also press on the fact that to verify that the hardware works, you don't need to have all of the software in place, because for example, to verify that I2C works here, it's really enough to send some data or read some data over the I2C lines. I, for example, don't need to have a full driver for the range sensor that I'm using. So if you are preparing software for board bring up, you should write the minimum amount of code needed to verify each part so that you can get a complete board bring up software in place as soon as possible. Because if it's one thing when it comes to board bring up, it is that time is of the essence, because the faster you're able to verify that the hardware works as intended, or that there is some issues with the hardware, the sooner the hardware designer can rework the design and order new boards. Because ordering new boards, while it costs some money, of course, the critical part is that it takes time for them to be manufactured and sent back, and can often be a driving factor of the timeline of a project. Okay, so let's now move on to the actual board bring up, and what I'm going to do now is essentially run through the different tests that I've created during this video series and see if I run into any issues. The first test I'm going to run is the test that blinks the LED to verify that the test LED works. So now I'm just going to build this test and flash it to the microcontroller. And I already know that this code is supposed to work since it can run on the launchpad, but now we will have to see if it also works on this other test target. So now I expect this LED over here to blink. Yeah, the LED blinks. So that test seems to be working. So let's move on to the next test. I'm not going to run this test because I can't really measure all of the output pins, or well, I could maybe do that, but I'm not going to do it. And I think I'm actually going to add a define here to only run this test on the launchpad. Same goes for this test. I should not run this on the actual PCB. Yeah, there's a bunch of test functions here that I can't, or that's not useful for me to verify the PCB. Okay, so then I can run the test for verifying the UART driver, and this will verify whether the UART lines actually works and are connected as they are supposed to be. So if I open the terminal now, I should expect to see these letters written out. Yeah, and I do. Good. So stuff seems to be working so far. Let's move on to... Yeah, now I've already verified that the tracing actually works, but so I don't really need to run this function to verify the UART, but I'm gonna run that function anyway, so it's better to just go through all of the functions. And then open up the terminal again. Yeah, and that works. Good. And in the next test here, I will verify whether the IR receiver on the PCB works, whether I can pick up the signal sent from this IR remote. So let's build and flash this and then try to send or press some keys. So that's going to be IR remote. And for this test, I'm checking this IR receiver right here, whether that's connected correctly. Okay, so open up the terminal again. So if I just press some keys here, yeah, good. Yes, that works. Can hold. Yeah. So that confirms that the IR receiver works. Good. And then I'm going to move on to test the motors, and for this I think I will just skip this test right here, the one that just sets the PWM signal, and instead jump straight to the one that tests the entire motor driver to confirm that all of the connections to the motor driver works. And for this I think I'm going to lower the speed here, the duty cycles, because I don't want the motors to be spinning at full speed. That's just going to be annoying. So maybe something like this. And then I obviously have to put the robot up like this so it doesn't drive away from the desk. So now if I build this, I should expect the motors to be spinning. Maybe I can show that as well. Yeah, good. So the motors are changing their direction and also the speed. So this verifies that the connections to the motor drivers work. Very nice. Okay. So then I can also run this next test here, test drive, which I don't really need to run for the board bring up either, because I've already verified that the IR receiver works and that the motor drivers work. But this is kind of a fun test to run, because it allows me to steer the robot. So let's do that now. Flash. So given that worked, I can move on to test ADC that are connected to the line sensors below the robot. So now I also need to find some white paper here. Something like this. And open the terminal again. So let's see if I do it like this. You can even see that the LED lights up here, which is a visual indicator that the white paper is detected. And I also get a lower reading on the channel 4 here. So if I remove the paper now, that value goes up. And I can do the same for all of these bottom sensors. LED lights up and channel 5 changes. Nice. And the front sensor. So that's channel 3. LED also lights up. It's really nice having these kind of supporting LEDs on the board while doing a board ring up, to get some visual indication on the board and not only just checking in the firmware. And then the last one. Yeah, so that's channel 0. Nice. So that works as well. Yeah, and then I'm going to run the next test, which is also for the line sensors. And this is more to verify that the code works, because I've already, with the previous test, verified that ADC works as it should. So now this is the back right. Yeah. Back left. Yep. And see, front right, front left. Nice. And then we might as well run test line as well. Then I can also open up the header file for this line, just to see. Okay, now the robot should be detecting the line in front right. So line front right. So that's value 6, and that's correct. And if you move away, line 0, it doesn't detect any line. Good. And if I just have it like this, it should be line front. Yep. This one here. And if I do it like this, it will be line back. That's also correct. Yeah, so that seems to be working as well. Great. And then I can move on to the I2C test. And this first I2C test here that I wrote in the last video just tests the front sensor. But let's just start with that one before testing the rest of the sensors. Terminal again. Yeah. So this is exactly as the last video. It reads the expected value from this front sensor, and it's also able to write the value and read it back. So it has connections to the front sensor. So let's run the other test that tests multiple sensors to verify the rest of the sensors, and also the interrupt line on the front sensor. Okay, so okay. Okay, so we're getting the value out of range now, even though I have my hand in front of the sensor. So this means that something is not working. So give me a moment to debug that. Okay, so I realized what the issue were, and that's inside the driver. Because right now in the test, I'm not starting the range measurements for all sensors, because as I said in the last video, I'm skipping the sensor on the left and right. But then in this function, I still wait for all of the sensors to finish their range measurements. But since the left and right are never going to finish, it means that we never get any values, or we never get any readings. So I need to add a case here, a define case. That returns true if we encounter sensor left or right. Like that. So then going back to test again, I'm also going to change a thing here. I should print fresh here as well. Like this. Okay, so if we build this again now. Okay, so now we're getting some readings here. So if I put my hand in front and further away, yeah, even further away, remove my hand, and if I put the robot up like this, I should get some out of range still. Yes. Yeah, so that seems to be working. And then I can also run the last test here. Okay, so now if I have my hand in front, kind of at the middle distance, I get front all mid. If I look closer, front all close, and further away, front all far. And if I move my hand a bit to left or right. Okay, so now it's a bit hard to get proper readings here since I have a lot of things in the way. But yeah, this seems to be working. Okay, so with all of these tests run, it means that I have basically verified all of the hardware. So this board bring up doesn't really give a true representation of an actual board bring up since it went so smoothly. Usually there are more issues than this. But now since I have a board that I've already verified before, it's kind of like a fake bring up really. But I just wanted to show you kind of the process of what's involved when doing a board bring up, or a very simple board bring up in this case, just so that you can get a sense of what it may entail and kind of the thinking process. What I'm going to do now before I end this video is that I'm going to take, since this video is going to end up being quite short, I'm going to take the opportunity to improve some things in the project. And I'm going to start by fixing a bug that I noticed while preparing for this video. And that is in the assert handler. Because right now when I assert, I send a trace. And in this function where I trace the assert, I'm supposed to configure the corresponding IO to mux to the TX pin of the UART peripheral. But what I actually do is I configure the RX pin instead. So I have to change this to bit 2 here instead. And the reason I didn't notice this before is that because most of the time IO init will have run, and this means that the pin is already configured correctly. But if the assert triggers before IO init runs, I mean in the beginning, like in MCU init, or when I initialize the microcontroller, I will end up asserting without a trace. So I need to change that here. Another thing I'm going to fix is a thing that I noticed in a previous video when things are not rebuilt properly. And the reason things are sometimes not rebuilt properly is because when I changed targets between Ensumo and the launchpad in this case, I'm just changing the define, and this define doesn't change the modified date of the file, which means that the make file doesn't pick it up, but the define actually changes the content of the of what's included inside the build, since I have several if-defs in the different files to select between the code for the launchpad and the code for the actual PCB. And the way I'm going to solve this is by having a separate build folder for the different targets. And to do that, I just need to change the path to the object files directory as well as the target directory. So here I'm going to add a subfolder named the same as the target. And also here, by just moving bin to here. And if I clean now and for example make launchpad and then make Ensumo and then move into the build directory, I have 2 different directories for the different targets. So now each time I switch between the 2 targets, the files will be rebuilt properly. And while at it, I'm also going to make some other changes to this make file. First, I'm going to add 2 new rules. One to start the terminal so that I don't have to write this line each time. So I can just copy this in here. That. And then I'm also going to sleep here for 1 second so there is some time to show what the command is. Not because I need it, but it can be nice when I do these videos for you to see what the command is that I run. And then also add some info about sudo. Okay, so now if I run make terminal, Oh yeah, I should also, yeah, I will fix that soon, but now I will just add a target. So now if I run terminal, it first shows the command and then it enters the terminal. So that makes it a bit more convenient to run as to start a terminal. And then I'm going to add a second rule for running all tests or building all tests. Tools, build test.h. You can also run that now. And these rules are just here to make things more convenient. Okay, but for this I don't want to run. I have to add a target. So I'm going to fix that as well. And they should also be added to phony, since they don't produce an output really. So that's going to be tests, terminal. The other ones should also be here, so address to line, forgot them before. Symbols and size. Size, yes. And right now, to exclude or to make goal not require the hardware target, I do that in quite an ugly way. So I will improve on this by adding these to a separate variable instead. I'm going to have a variable called goals without hardware. Gonna be clean, CPP check, format, terminal and tests, and then I'm gonna check if goal has target by using the filter function on this variable. Okay, so this is basically going to become true if the goal is not part of this list here, and then I can just add an if equal. This is kind of an ugly workaround, but that's usually how it is with make files, unfortunately. So if goal has a target, then I should run this here, and now I can remove these as well as this. So like this, and just add an end if at the end. So this makes it a bit cleaner than before. So with this in place, I should be able to make terminal without supplying the target. Yes. And if I try to, for example, just run make, it should force me to add a target. Yes. And yeah, maybe I just add a test like this. Test blinking LED. Yeah. So that works. And one last thing I want to change is this here. So I'm going to add a variable called main file. Move this down. And like that, since I have a different make file depending on if I'm building the tests or not. So then I can have main file here, and instead of deleting this object file, I'm going to run touch on the source file instead. Like this. Can add a comment for that too. And finally, I also want to update the CI file or the GitHub action file. First, I'm going to create env here. Then I'm going to add tools path here instead, because this will allow me to not repeat myself down here. And here, instead of running it like this, I can just do make tests now. Let's just try to run make tests here again to see that it works. Yes. Okay, so that's all of the changes that I'm going to be doing in this video, and really the changes I did now has nothing to do with board bring up. I'm just taking the opportunity to make these small improvements in this video. So let's commit this code now. First CPP check though, and format. And then I'm going to create several commits here, I think. So first one for the build. That's gonna be GitHub. Well, I should first actually create a local branch. Bring up. And then I want to add the build related changes. So that's going to be the CI file and the make file. Like that. And then I can add the fix for the assert handler, the assert trace. Yes, and finally the test related changes. And then I can push it. And check to see that it actually passes the CI system. Create a pull request. Can also go into the details here to see that it runs my new steps. And yes, it does. So it ran successfully. So let's see if we can go into this pull request. Yeah, so now I can just rebase and merge this. And that's it for the code in this video. This board bring up went very smoothly for good reason, since as I said before, I've already verified this board and I have so much code in place when doing the board bring up this time, so it's almost expected to go smoothly. But I was still a bit surprised that all of the tests worked so well without any modifications basically. Overall, I think board bring up is a fun part of developing an embedded system because it's always exciting to see if the hardware works, but also of course stressful, especially for the hardware designers. But it's just a stage of the development where you as an embedded software engineer at least get very close to the hardware. But that's it for this video, and from now on I will not be using the development board anymore and just run the code on the actual robot, or well, I'm going to run some simulations on the host computer, but other than that I will not be using the development board anymore, finally. But that was it for this video, so thanks for watching and see you in the next one.